Hello. Now that we're experts on IPs, we can start connecting things. So, we're gonna have to construct some way to tell the socket which IP to connect to. And in the end, we're gonna call this connect function. If we look at it, it has socket as this first argument, and that's just which socket we're gonna connect with. Then we have the SockAddress pointer. Okay, so that's the actual address to point to. And then we have nameland, which we'll get to these in a little bit. Actually, we'll get to this one now. So the first idea is to make just the SockAddress struct, right? It's pass it in. How hard can it be? However, since this is a C library, it's within a C, that means it's a bit tricky for it to handle a bunch of different addresses, right? So you might want to connect this to IPX, or you might want to connect it to, with IPv6 or IPv4. There's a lot of options here. So the way they have decided to structure this is that they have one base struct, which is SockAddress, which doesn't really contain anything. And then what you do is that you make another struct, which is specific to your type of connection, if it's IPv6 or IPv4 and so on, you make that. And then you just cast it to a SockAddress pointer and pass that in. And then it will figure out, in the bowels about like, okay, did you actually use a IPv4 or IPv6 or, IPX, what did you use? So that's why that looks like it does. And don't be confused, because we're not actually going to be making a SockAddress struct, we're going to be making a SockAddress in struct. Con address. All right. So the SockAddress in is responsible for doing IPv4 addressing. So IPv4 socket addresses. Internet style, baby. Let's go. And if we go look at it, you can see it's quite sparse. Not that much in there. So we have family, and that's just which family the SockAddress is working with. And I believe this is used to determine what kind of struct it is, but I'm not quite sure. But anyway, then we have the ports, which we're experts in. We know what ports are. And then we have the in-address struct. It's another struct. And that's going to contain the actual address, the address part of the address. It's a little bit confusing. This is called SockAddress. And then there's also address, but whatever. So let's go check this one out, all right? So here's in address, and this is containing the actual 4 bytes of the IP. And it looks like a fucking mess, because this is C. And it's more specifically, it's Windows C, so it's gonna be shit. So we have a union. That's cool. So it's a union. And what that allows you to do is reference the address in multiple ways. So you can either address it as just 4 bytes. Here, just the 4 bytes STR. Or you can reference them as 2 words. Or 2 shorts. And here you can reference it at just 1 integer number. And the name suckass, so they've added defines here to let us use shorthand each of these options, right? So we have like S-address for addressing it as just an integer. Then we have like here's net, which is the first byte of the IP. We have host, second byte, and so on. You can also address it as a word. Not the first word though, it's a little bit confusing, but okay. Yeah, so big mess. Let's go away. So I will elect to construct the byte or the bytes as an integer and pass that in, so I don't have to juggle the union way too much. So what I'm gonna do is that I'm actually gonna make a char array, unsigned char, IP bytes. And I'm just gonna align the bytes like this is like 1, 2, 7, 0, 0, 1. So now I've constructed the bytes that I want to pass in here. So just in order, 1, 2, 7, 0, 0, 1. Very nice. And then I'm gonna cast this to an integer. And I'm gonna have to do a little bit of pointer magic here to actually convert these 4 bytes. And he's like, just treat it as an integer, So I'm just gonna do an unsigned integer IP, and that's gonna be equal to. First, I'm gonna cast. Whoops. I'm gonna cast the IP bytes array to an unsigned int pointer. Right, remember, since this is a C-style array, like it's just an array here, static array, that means that IP byte is gonna be a pointer. It's gonna be a pointer to the first element in the array. So I'm just gonna cast that pointer to an unsigned int pointer and essentially tell C++ this, like, okay, those bytes that you had, they're ints now. So that means every time I read from this unsigned int pointer, it's just gonna read 4 bytes and treat that as if it's an int. So that's great. So I'll just do that. So I'll just dereference that bad boy. So I'm taking the array, converting it to an unsigned int pointer, and then I'm dereferencing it, which would mean I will dereference all of these 4 bytes and treat it as if it was an int memory-wise, and just copy that over into our IP variable here. No problem with that. If it doesn't make sense, it's okay. It is what it is. I would encourage you to go over this in your head to try to understand what's going on. All right, so now we have our IP in int format. So now let's start filling up these structs. So we're gonna have the family, and that's gonna be AFINet. It's the same as the socket. And then we have the SYN address. And like I said, I was gonna use the helper macro here, this SAddress one, to reference the integer representation of the bytes. So I'll just type SAddress here, equals IP. Fantastic. And then I'm gonna put in the port. So we have SYN port equals, and let's check out what the port actually was. Oh, I haven't even started the server. Well, I'm dummy. So let's start the server. There it is. So now we have a server going, and its port is 35000. Okay, so that's the port that shows. So 35000. Great. So now we have our IP structure set up. We should be able to connect. So let's connect our socket that we made, and we want to connect it to this con address. And again, it wants a sock address pointer and not a sock address in pointer. So if I just type, address of con address, it's gonna start complaining because, hey, our sock address in is not a sock address. So it doesn't know that there's a link between these two types because this is C. There's nothing as, inheritance or anything like that. So we're just gonna have to coax it a little bit and just cast it to a sock address pointer. We know what we're doing. And then for the namelen, that is simply to help the function figure out which type of socket address this is. If we're using v4 or v6 and so on, and also to find out, if they're gonna change versions. I believe they will look at the size of the structure to determine, okay, which version of WinSocket are you actually using. So we just need to pass in the size of that struct. There we go. So size of con address to help the connect function figure out what the hell is going on. All right. So connect will return an integer, and that's going to be the results, the result of the connection. So we'll just save that int connect result. And now connect result is going to be 0 if the connection was successful. So if everything went to plan, connect result will be 0 here. It will return 0. However, if it wasn't successful in any way, it will return -1. I think it's kind of undefined actually. It will return something other than 0 to tell you that, okay, something went wrong here. So I'm just gonna check if connect results, and I can if this because if again integer will return false if it's 0, and if it's not 0, it will return true. So it will just check this integer and say, is it 0 or not? If it isn't, then run the if sets. If the body. I don't know. I'm tired. Okay. So if we have an error, which means that connect result will not be 0, then we want to print something. So print connect failed. Oh no. I'm going to return 1. So let's run it and see what happens. Okay, so we failed. So you see that it kind of took a minute there. So it definitely tried to connect. We didn't, pass in anything weird here. It just kind of didn't. It couldn't connect to anything. To actually get the error code to figure out, okay, but what went wrong? we can call VSA get last error. And this will just give us the last error that happened within, the VSA library as an error code. So let's run it again and see what error code we get. Okay. 10061 is the error code that we got here. So let's go and look up what that means. So I'll just go into this MSDN here. You can use Google VSA error codes. You might realize it's not my first take. I fucked up. So VSA connection refused is the error code here. 10061. That's the current code we got. Connection refused. No connection could be made because the target computer actively refused it. How rude. This usually results from trying to connect to a service that is inactive or the foreign host that is one with no server application. I think I read it out weirdly, but whatever. Okay, so we got a connection refused, which is different from connection timed out. So connection refused means we reached some sort of host, but they didn't have a socket for us. Either, that port that we're trying to connect to currently isn't tied to anything, or perhaps, the socket that someone has bound to that IP and port doesn't accept connections right now. Meanwhile, the connection timed out simply means, nothing was found. Your internet is down, or the PC you're trying to connect to just doesn't exist. But we got a connection refused, which is good, because, I connected to the local host, so I would be pretty freaked out if it said, that computer doesn't exist. I'm like, what? No! I'm here! I exist! So the problem isn't actually anything with the server or with our client. The problem is the port here, because we are going to have to talk about a fun topic called endianness, or byte ordering. All right, so strap yourselves in for an action-filled explanation time. So in your computer, if I make an integer a is equal to 16. Sure. Sorry, I'm brain fart. Okay. How that integer is stored in memory is important. So let's say we do something like, okay, so a is 16, it's an integer, so that means 4 bytes. 4 bytes. How would we store that? So let's say somewhere in memory, it's like a bunch of shit, and then comes our 4 bytes here. And that's supposed to hold our integer a. How would each byte of the integer be stored? Well, let's say we split it up like this. Let's just say we write it in sort of order. So I'll do 16 here. So that's the first byte. Since the number is smaller than 256, it actually fits in just 1 byte, even though the integer takes up 4 bytes. So the rest of the bytes will just be 0. Maybe I should have picked a better example. Oh, excuse me. So the first byte will contain 16, and then the upper bytes will just be 0 here. Now this ordering that I've done, that the least significant byte is first in memory, is something called big endian. No, this is little endian. Little endian. Little endian. Alright. It's called little endian. I have no idea why it's called little endian. I prefer least significant bit first. Or least significant byte first, because that actually explains what the fuck it is. Well, little endian. What I was supposed to do is a little at the end. No, it's in the beginning. Okay. So yeah. So that's little endian. Alternatively, we could store it like this. So we could do 4 bytes. And instead of putting the byte 16 at the beginning, we put it at the end. 16, 0, 0, 0. And this is kind of like, this kind of makes sense, right? This is how you would write the number. Like if we wrote this as a hexadecimal number, it would be like 0, 0, 0, 0, 0, 0, 1, 0. Like that is how we would write the number, like if I was coding in C++ or whatever. So it kind of makes sense that, okay, we align the bytes in the memory as they're written, like, you know, on paper, so that the memory matches the data. And this is called big endian. Big endian. Or most significant bit. Most significant first, I would say. Significant first. All right, and this I will write least significant first. Which I personally think it's a better name because it explains the fuck it is. All right. So yeah. Operating systems these days, like Windows and Linux and so on, has opted for the little endian system. That is a standard for operating systems. They put the least significant byte first in memory. And then as you move up one, they become more and more significant. And significant means just how much does a change to this byte change the actual value. So if I plop this down to 15 instead, so it's like do 15, then I've only changed the actual value by 1. But if I plop this one up to a 1, so from a 0 I put a 1 instead, now I have changed the number by a huge amount, right? Because this is a very high order bit. So, you know, it will be like putting up 1 here at the number. And it will become this huge number. Yes. God, my brain is trying to chase down thoughts. Okay, so little endian is a default for Windows, right? But could you guess which is the default for the internet? It's big endian, baby. Yeah, let's go. We have to switch endianness because we want to talk to our friend. Yeah, so this is the problem, right? Windows stores all of its values in little endian while the internet is communicating in big endian. Problem. And specifically, that's a problem for us when we're trying to enter the port here, because we're typing 35000, which of course in Windows, being little endian, that's gonna be I think it said like little Indian. We need to convert it to a big Indian. Okay, 35. Okay, there we go. So here we can see that the hexadecimal version of 35000 is 88B8. 88B8. Right? And B8 is going to be the low significant byte of that value, which means it's going to be stored first. So here's going to be B8. And then it's going to be 88. And that's what we're sending off to the internet to do its thing. And of course, when we read this, we know that this is the low order byte, this is the high order byte, this is clearly 3500. This is clearly 35000. But when the internet is looking at these 2 bytes, it's doing the opposite. It's saying, oh, this is the low order byte and this is the high order byte. And that means you're trying to connect the port once again. You're trying to connect the port B888. You're trying to connect the port 47,240. That makes sense. So it's saying equals 47,240. simply because they're reading the bytes in the wrong order. Problem. So yes, this is the big endian, little endian debate coming back to haunt us, right? We thought we decided on little endian, but the internet, of course, decided something else. So what we need to do is that we manually need to make sure that this port here is actually translated into big endian, so we connect to the correct PC, all right, or to connect to the correct port. And the way we do that is very simple. We use write host to network short. There we go. So we call the buttons function, which is host, which is us, to network, which is, you know, the network system, short. And this will convert a short number from host NDNS, which is, you know, the NDNS of the computer, to network NDNS, which is, you know, whatever the NDNS is on the network or on the internet. So now we have our 3500. It will swap the bytes so that it makes sense for the internet, and then we're gonna run it. Let's go. Hey! I mean, okay, we didn't write anything, but let's check the server, right? Hey, look at that. Something connected, and that's us, baby. Let's fucking go. Okay, so we managed to get over the hurdle of little NDNS and big NDNS. And now we managed to connect to our server. Yes! Okay, and now you might wonder, why didn't we have to do anything for the IP? You know, we wrote the IP here and it worked just fine. But if you think about it, if we think about the IP, like, okay, so here we have the IP, right? We have the 127.0.0.1. If we think about this as an integer, you know, if we were to write this into memory and convert it to an integer, God, I can hear you laughing at me. Don't write in Discord if you're here. If you're here and you're listening through this, don't write in Discord. Okay, I don't want to know. We're gonna forget about that. Okay. It works. Woo! Oh, train wreck. Listen. I'm so sorry. Oh God. Okay, we're just not gonna worry about that for now. Okay. Woo. All right. Anyways, the point was supposed to be that we already wrote it in big endian, so that was the point. But I couldn't figure out how to make that point. Whatever. Let's actually take a step up. Okay. Left time is over. No more jokes. We're on to the next level, okay? So we're actually not gonna connect to localhost. We're gonna connect to one level higher. We're gonna connect to a local network IP, okay? So I'm gonna dox myself for a sec and check what my IP is. I'm just gonna run ipconfig, and there it is. There's my local network IPv4 address. So I'm just gonna type that in instead. Not in that way. Okay, I got a concept. There we go. Okay, so now I'm not connecting to localhost anymore. I'm actually connecting to my own local network address. So let's run the server and let's run the program. Okay. Okay, so it didn't work. Yeah, because I'm a fucking idiot. I put 1 here. That's not my IP address. That's the gateway. This is my address. 102. 1. Oh. It worked. Oh, well, there we go. There we go. There's a connection. Okay, you can also see that the IP that I got that I connected is actually now also in this local network form. So when you're connecting to a local address, it will give its own local address as the source of that connection. So that when we're looking at an IP, we can actually see where that, what layer that connection came from, which is quite nice. Great. Let's take a step up, okay? Gonna take 1 step up. Now we're gonna connect to our internet address. Okay, so we're gonna step out of our local network, and we're gonna step into internet zone. I'm not doing it at a take. I'm sorry. I'm so tired. I don't remember what my password is. Password 123. Let's go. Don't dox me. And I'm just gonna set something secret up while you guys are waiting. There we go. Okay. So here is my router. And on the router, I can actually see what my global IP is. So remember from the chart in the previous lesson, this is going to be the router's address on the internet, right? So this is the address that it's referring to itself as when talking with other routers. So if we try to connect to this address here, it's going to be 46, 39, 122, 74. There we go. Connecting that address with this port. What could fucking possibly go wrong? So I'm gonna restart the server. I don't need to restart, but I do it. So let's try connect. And it's trying so hard. There we go. Connect failed. Okay, so we couldn't connect. And this is actually because, remember from the previous lesson, when we started reaching out of the local space, where, the local network, suddenly you can't talk to computers. Specifically, you have to provide a port for your router to forward to these specific computers. You have to open up ports, and now we're gonna do that. So this is just my router. So I just connect to its local address in the local network, and usually you have this little UI that you can interact with, and it can do a lot of things. So here I'm gonna go to NAT forwarding, port forwarding. I remember I said there was this table containing all the port forwarding options. So if I want to send some traffic from one port into one specific computer on the local network, here is that list. And I'm going to add myself. So this is going to be FG Network. So let's use that name in the list, doesn't matter. Then we have the device IP address. So this is where it's going to send the traffic when it comes in at this port. So I can just click ML desktop here. So that's going to be my desktop. And as you can see, the IP here matches what my local IP was, 102. And then the external port, so that's the port coming in. So if something is connecting to me, it's going to read, okay, did you try to connect to this external port here? And for us, it's 35,000? Yeah, 35,000. So if something comes in with a port of 35,000, we're going to forward that, and then the internal port is just, should it translate that port to something. So if I do 5,000 here, if a connection comes in at 35,000, I will continue, the router will feed that forward, but change the port to be 5,000. So this is like if you have some port issues going on, like you have a collision or something, you can sort of alias and port in that way. But in our case, I just want it to be the same. Protocol, we're not going to look at this now. Save. Okay, so now I've added to the list that any traffic that comes in on port 35,000 should be forwarded to this IP here, to this local network IP, and that's going to be my computer. So that's the list, and let's see if it works. So I'm gonna go. Hey, it worked! Hooray! And now you can see also the IP of the connectee, or the thing that was connecting, has also been changed to be my external address. So you can even see here that, okay, this connection did not come in from the local network, it is an internet connection. Fantastic. I have a feeling I'm gonna have to explain a lot of this again. So, you know what? Put in Discord. If you want me to explain something better than I did now, you say so and I'll make another video, okay? When I'm fucking not fried in the head. But the worst part is over now, okay? The worst part is over. I feared I was gonna have to talk about little endian and big endian, and I had to, but okay, it's fine. Now it's over. So we have a connection. Fantastic. Okay, so now we're gonna talk about how to actually use the connection to send data and receive data. So the hard part is over. Now begins the fun part. We're gonna make games. It's gonna be fine. Okay. I'll see you guys. I'll see you guys next time. Bye.